My name is Donovan, and I'm a NodeBots addict. I got hooked at NodeBots Day in Austin, 2013, so thank Cassandra for that. I was really excited by how easy it was to interface with hardware. I'd tried a little when I was younger, and it was pretty hard. I couldn't quite get it. But once I encountered Johnny 5 and I saw how easy it was to start doing things, controlling servos and LEDs and whatnot, I got really pumped. And I decided, of course, that I wanted to build a robot. So I'm driving home, and I'm thinking about all the great things I'm going to do with radar dishes and lasers, and it'll get me a beer and all this stuff. And I got home, and I started researching what would be best. And I found hexapods online, and I thought, well, that's cool. That should be easy. It's got 6 legs. It's not going to fall over. But I was wrong. Rolling robots are easy. Walking is hard. It's really, really hard. I was surprised, because I'm pretty good at it. I thought the robot could do it too. But there's 2 big challenges that I didn't think about. First, there's 2 broad categories of gates, robot gates, static and dynamic. Static gates are those gates where the feet of the robot are in touch with the ground. They define a polygon. The center of gravity stays over that polygon. That's a static gate. The dynamic gate kind of does the opposite. It's able to move outside that polygon. It'll counterbalance, or maybe while it's falling, it'll get another foot out in place and catch itself. But I stuck with static gates, and I stuck with a hexapod because I thought static gates would be easy. But that's not necessarily true. If you have 6 legs and 4 of them are back a little, back past center, you lift a front leg, it's going to tip over. So that made it a little complicated. There was another thing that made it also very complicated, and that's robot anatomy. This is a leg from this hexapod, and let's pretend that my arm is that leg. You've got 3 servos controlling that leg. You've got a coxa servo. It kind of does this movement here. This is the femur of the robot. You've got a femur servo that does this movement. And the tibia, you've got a servo that does this movement. The other important part to remember is the end effector. That's the part of the foot that comes in contact with the ground. So you've got these 3 moving parts. Here's an overhead view of the same components. And I thought that all I had to do was put the coxa in contact with the ground, put the end effector in contact with the ground, move that coxa, and the robot would move forward. But I was wrong. Now, the end effector, when you do that, the end effector describes a circle with its center of rotation, with its center on the coxa's center of rotation. And if you have 6 legs all doing that with their own circles, the robot, well, it looks drunk. It's sloppy. It's sliding around. It's pushing its toes across the table. It's kind of a mess. And to make it work, you have to get a straight line going with your end effector. So yes, you have to move that coxa servo to get it moving front to back. But you also want to keep that end effector in line, so you've got to move the tibia back and forth. But when you do that, the end effector relative to the ground starts moving up and down, so you've got to move the femur as well. So to move that one leg forward while it's in contact with the ground, you've got to move all 3 servos in concert. It gets pretty complicated. And then if you think about there's 6 legs, each one has 3 servos, that's 18 servos that are all having to work together to make this robot go forward and not look like a sloppy drunk. So that's actually a lot going on. 18 servos, and we're animating. And the way Johnny 5 works, you've got the control code is running on a host server on your computer, and you're communicating with the Arduino on the robot, your microcontroller, over USB or Wi-Fi or radio, or depends on your configuration. But even over USB, I was thinking that's a lot of commands to be sending to a servo, and we want to do it fairly frequently. We want this thing to walk smoothly. It's 30 frames per second, I guess, is a typical animation speed. Even that's not really fast enough for these robots. So I was kind of freaked out. I didn't know if it was going to work, but at Empire.js this year, Rick Waldron gave a talk. Is that thing playing? Okay, good. Rick Waldron gave a talk called Bits of NodeBots Next. And he was able to demonstrate that, yes, it is possible. He's got that quadruped there. It's got 4 legs with 3 servos each, 12 servos. At the time, the servo class had a default frame rate of 100 frames per second. So in this 8-second clip, he's sending almost 10,000 commands to the microcontroller moving these servos. And I didn't have to send them all, but roughly 10,000. So, yay, it works. It's possible. I mean, JavaScript developers, especially client-side developers, know that it's possible because we do JavaScript animations in the browser all the time. But, could Fermata handle it? Could node serial port that handles communication over USB. Good Formata on the microcontroller handle it. The microcontroller itself, it's not a supercomputer. It's $45. If it was, we'd have a lot of them. So really impressive that it's possible. But Rick had to roll all of his own animation code. It was a lot of work. It wasn't as bad as set timeout 10 milliseconds, go here, set timeout 12 milliseconds, go there. It wasn't that bad, but still, it was a lot of work. And we wanted to make it more accessible and easier for people who are working in NodeBots to do animations with devices over time. These are scripted animations. So it's in Johnny 5. It's called the animation class. It's fairly new. It gives you a lot of things that you might have seen if you've worked in any traditional animation programs. It gives you a timeline, cue points, keyframes, easing and tweening. Let's take a look at a animation program. This is from Adobe Edge Animate, and I just wanted to show their interface. There's a big stage where you put the objects that you're going to be moving around. There's this timeline at the bottom. So you've got a timeline, something that represents the progress from 0 seconds to whatever the end of the animation is. And you've got a target, the list of devices or objects, in this case, that you are moving around on the stage. So we also have cue points. Those little diamonds represent static points in time where we're going to be doing something. And then you've got keyframes on the dark green row. You can see we've got little degree values. Well, you probably can't see it. It's really small. But there's little degree values assigned to certain objects on the stage at those cue points. And then we wanted to do tweening. So you set a beginning point and an end point, and it calculates all the frames in between for you, of course. And easing, if you've done any animation, you know that easing adds a degree of realism to any animation that you're doing, or a degree of naturalness. If you do a linear animation, there's no acceleration or deceleration going in and out. It doesn't feel right. But if you add easing, where it accelerates in and decelerates out, it gives it a much more natural, believable feel. So we wanted all these things that are present in traditional animation programs, but we don't have a GUI. We don't have a GUI at all. We have to do it all in code. So I'm going to show you guys how we represented that in code. We're just going to step through it really fast. I know it's grayed out. Don't worry, it'll show up in a second. But this is a complete program for doing an animation in Johnny 5. So first we require Johnny 5, just one module. We create a board. So Johnny 5 is really cool here. It goes out and it finds the device that's most likely your microcontroller on the serial bus. You don't even have to set an address. It finds it. It gets Formata on the host server, Formata on the microcontroller talking to each other. They set up communication and a ready event is fired. Now we can do stuff in Johnny 5. So first thing you want to do is create the objects or devices that you're going to be animating. So we've got two servos here, one called right, one called left. One's on pin 10, one's on pin 11. I want to point out real quick, just as an aside, that we've already done everything we need to do to control servos in Johnny 5. It is incredibly easy. 4 lines of code. We've got 2 servos. I could call write.to TO and then pass a value 120, and that servo is going to go to 120 degrees. I can inject these 2 things into the REPL and start moving them around from the command line. So it's really easy to get stuff happening in Johnny 5. Next, I use a servo array. Servo array is a feature that was built into Johnny 5, and yes, it's an array of servos, but it adds the ability for you to call methods on the servo array and have them in turn called on all the members of that array. So that's a nice convenience thing. We're using it here to create a target. The target being that list of devices that we're animating, that were on the left of that timeline. Next, we create an animation. So when I create an animation, I just pass it a target, a default target. You can override that later if you need to. But pass in a default target, and now this timeline exists. There's no commands or instructions on it yet, but that timeline exists with the elements that we're going to be animating. Next. Whoops. Yeah, next. So like I said, there's no instructions on that animation yet. To get instructions there, we have to create what's called an animation segment. An animation segment is a series of moves that compromise some larger movement that you want to modularize. Good examples are sit, stand, walk, turn. Things like that make good animation segments. So you call the enqueue method on an animation, and you pass it an object. And that object can be defined in a variable. It can be defined on the fly based on sensor input. You can do a lot of fun stuff with it. But I'm just passing an object literal right now. So one of the properties you have to pass is a duration. How long is this animation? And I passed 5,000. That's a millisecond value, so this is a 5-second animation. Next, an easing function. You can have an easing function on the entire timeline. So from beginning to end, that playhead is accelerating and decelerating, or using whatever formula you want to use. We used T.J. Holloway-Chuck's ease component in this, so there's a lot of easing functions available. You can also ease between two keyframes, so you've got a lot of control over smaller sections of the animation, so you don't have to ease the whole thing, you can ease just one little part of it. Then we have to define our cue points. Our cue points represent points in time on that duration. Their values from 0 to 1, they represent a percentage of completion, so 0 is at 0 milliseconds, 1.0 in this case is at 5,000 milliseconds, and we've got a lot of steps in between. There's really no limit to the number of steps you can have, but you want to keep it small. That's why animation segments and not one big animation. Next is the keyframes. Keyframes is a two-dimensional array. The first dimension maps to the objects or devices that we're animating. So the first row of this array is mapping to, what is it, right or left? Is mapping to left. And the other one's, it's mapping to right, and the other one's mapping to left. Then within each of those elements, we have another array, and they map to the cue points. So on the first row, the first element is mapping to the first cue point for right. The second element is mapping to the second cue point for right. These are the values for the servos at those cue points. I want to talk a little bit about what these different things mean. So in the first frame on both of these, I've got null. And what that does, it tells animation to not set a value here. Just use whatever value the servo is currently at. When you're walking, you don't know where your legs are going to be when you start walking. So you just want to start from wherever it's at, and it'll adopt that value. Johnny 5 keeps track of where the servo was last set to, so we always know what that value is. And the second one, I've passed an object with degrees 110. Obviously, that's going to move it to 110 degrees. Next, we've passed in minus 90. If you pass in a number value, that's a step value. It's going to just move the servo backwards 90 degrees or minus 90 degrees, so that's going to take us back to 110. Excuse me real quick. Next, I call false. That says do nothing. Just leave that servo where it is for now. And then degree 0, so obviously it goes back to degree 0. Second line is very much the same. The only real difference is I've got null somewhere there in the middle, the third element. Putting null in between two keyframes says skip this cue point for this element at this point in time, don't do anything, just pretend it's not here, animate over it. It's going to animate from the prior keyframe to the next keyframe and pretend that one's not there. So you don't have to define a keyframe for every single element at every single point. A lot of other features and options available in animation, so I don't want to overcomplicate this because it's as easy as it seems. So let's talk about some gates and actually moving the robot. This first one is the wave gate. And is it animating? Okay, good. If you see a dotted line there, that means the leg is lifting up and moving forward. Don't really have to worry about that whole end effector problem in that case because they're off the ground. But if you have a solid line, it's moving backwards. So after I've moved the legs in pairs, all 3 pairs, I move all 6 legs back together at the same time, all 18 servos working in concert. So let's give it a shot. Fingers crossed. Okay. Let me see what gate we're set at. Okay, so this is the wave gate. Should move this. Is it caught? That was close. A long walk off a short table. All right, let's try dangling it over here instead. Actually, let's do this. So, there it goes. All right, so we want the wave gate. Sorry, I have to change it back. Freaked me out a little there. All right, so we're moving the legs in pairs, and we're walking forward. Thank you, thank you. All right, so let's move it back. Next gate I want to show is a crawl gate. This one's nice and conservative. I probably should have mentioned this. Servos are really expensive. That's weird. I'm using this leap, and it's got ghosts. I haven't had this happen yet. So I'm going to stand close. The servos on this thing are really expensive. So anytime you're using a gate that's got them lifted up off the ground, moving a whole bunch at a time, and there's only a few in contact with the ground, they're carrying a pretty big load. This thing's pretty heavy, heavier than it looks. And if you're impacting the ground really hard and carrying a big load, you will strip your servos, no matter how good they are. And that gets really expensive really quick. So this is a conservative gate that only lifts one leg at a time. But all the other time, all the other legs are moving. So let's see. Good. What gate are we using? Okay, so this is crawl. So I feel it's important to remind everybody this is all Johnny 5 JavaScript running on Node. We've got an Arduino Mega with just an extra shield on board, a little $20 shield, so this is not some over-the-top investment. Next I want to show the walk gate, and I didn't even bother with a new animation for this because it's just kind of mind-blowing. But what happens is, that is freaking me out. Okay, what happens is when we start our walk, one leg comes up in the air, and it gets to its inflection point up at the top, and then we start moving the second leg. And when that first leg gets down to the ground, the second leg is at its inflection point, and we start moving the third leg. So you've always got two legs off the ground, but they're on opposite sides of the robot. They're on opposite sides of the robot. This is my favorite gate. It's not too aggressive, it doesn't damage the servos, but it gets the robot moving forward at a reasonable speed. It's me. The way I'm holding my hand. I'm using a leap motion controller, by the way, as well, which is really cool for robots because it gives you a lot of flexibility, but something about this it doesn't like. So here goes the walk gate. So two legs off the ground at all times, four legs in contact with the ground. Again, all 18 servos working together. And there's also what I call the run gate. It's actually a tripod gate. And that's where we're moving the legs in two groups. Three are on the ground, three are in the air. That's the one that's really hard on servos, and I've blown a few $100s in servos. So that's the walk gate backwards. So I use that one sparingly because it is rough on the robot. So turning. Remember how we were talking about how you have to keep that end effector in a straight line when you're walking forward. Well, with turning, it's a little more complicated because you have to describe a circle with all of the end effectors around the same point. They have to be concentric. That point could be anywhere. The robot could be turning in a big circle, but obviously it's easiest to do it on the center of the robot. That's what I've done here. So turning, all the end effectors have to describe their own circles that are all concentric. That's a little tough, but it'll do it. So let's see here. Walk a little forward. Okay, so that's turning. So, thank you. About the leap motion controller, I'm just going to do a tangent here. They're a hardware developer, and they really want us to build stuff with this. And I know that they really want us to build stuff with this because their API is awesome. They've done a fantastic job. I encourage you to check it out. Even if you can't think of a practical use, it's a lot of fun. It's a really cool device. And again, all hardware manufacturers should strive to do what Leap has done with their API. Okay, so, we're going to try a cool trick with a Leap here. There we go. Okay, good. Let's shut it down. So how am I? Oh, I'm doing pretty good on time. I'm going to close with contact info. Donovan Buck, I don't have to lie. I'm DTEX at GitHub and Twitter. There's a new forum that Chris Williams set up for NodeBots. It's forums.nodebots.io. It's relatively new, so there's not a lot of content in there yet. But I can promise you that the core Node people check that every day. If you have a question about NodeBots and it doesn't qualify to open an issue on GitHub, and you don't want to mess with IRC, you can go here and your question will be answered by the people who really know what they're talking about. So that's a great resource. And I want to just leave y'all with, like I said, I was really excited about how easy it was to get into hardware. I really have no idea what I'm doing. I don't know anything about electronics, but I made this, and that's pretty exciting for me. But you can too. And, there's this whole Internet of Things, cloud, blah, buzzword stuff going on. But there's some really cool opportunities as well. There's no group of people anywhere more qualified to do amazing things with hardware and the internet than this room. So please go out there and do it. Give it a shot. Go to a NodeBots event. Go to a NodeBots Day event. You get all day. You can do more. It's a lot of fun. It's very rewarding. And please, check it out. So thank you all.